In quadrupole magnet, G was the gradient and which is a constant quantity. In sextupole magnet, rather than G, the derivative of G is constant. Means second derivative of the field is a constant quantity. Because it is a parabolic curve, depends on the x square. So second order derivative will be a constant quantity. Means magnetic field will vary with s by 2 x square minus y square, and horizontal component of the magnetic field will be sx. Now you can see here in the horizontal component x is multiplied by y. Means this sextupole magnet will generate coupling in the betatron motion. Means horizontal motion will be coupled by the vertical betatron motion in the presence of the sextupole. Now we can calculate the kick of a sextupole also, as we calculated the kick due to quadrupole. So again the same formulation will be used. Magnetic rigidity is here and By dr. This formulation for computing the kick has been used many times. Now at the place of By we will put this value. So this will be ml x square minus y square. Here m will be s by b. So this will be half ml x square minus y square. Now because we are introducing this sextupole magnet at the place of non-zero dispersion, means where the dispersion is finite, means displacement of the particle from the design axis can be written down as the displacement due to betatron oscillation and displacement due to dispersion into delta p by p. Now we will put the value of x in the sextupole kick. So this will be half ml, and at the place of x we have written down this. So the square of this quantity plus y square. In vertical plane there will be no dispersion because we are considering that bending in the synchrotron is taking place in the horizontal plane only, and dispersion will be only in the plane of bending. So in vertical plane there will be no dispersion, so we have only horizontal dispersion in the case of a synchrotron in general. Due to imperfections there may be vertical dispersion also, but in this course we are not considering imperfections in the lattices. Means we are considering only perfect lattices. So when we will open this bracket, we will have x betatron square, d square plus delta square, and 2dx delta and y square. Now you can see that this term here depends on x into delta. This is the similar term which we have seen in the case of a quadrupole. Means this term can be used to cancel the term generated by the quadrupole. And if we can cancel that term in the quadrupole kick, then chromaticity can be corrected. And these are extra unwanted terms due to sextupole magnets. So sextupole magnets corrects the chromaticity, however it generates various unwanted terms. And you can see that these unwanted terms depends on x square, delta square and y square. Means our dynamics becomes non-linear when we introduce the sextupole magnet in the machine. How we can calculate the chromaticity? Now we quantified that what is the amount of the chromaticity if we know the lattice, or if we know the twist parameters or the strength of the quadrupole. Can we compute the chromaticity? We are going to derive that formulation. Now suppose this is a complete path in a synchrotron, design path, and there is one quadrupole, and we are looking the effect of this quadrupole on the off momentum particle. Because up to the quadrupole dynamics remains linear, so if we will calculate the effect of one quadrupole and we can quantify it, then for all the quadrupoles effect will be superimposed. So we will calculate the effect of one quadrupole on the off momentum particle. So let us say that this quadrupole has the transfer matrix MQ, and after this magnet and again reaching to the beginning of this magnet, the matrix is MR. So if we multiply these two matrices, we will get the one turn matrix or a matrix for the one complete turn in this synchrotron. So this is the M, one complete matrix for the one complete turn, and these are the matrices multiplied. Now we want to see that if strength of this particular quadrupole has been changed, what will happen? So let us say that the one turn matrix has been changed to M with subscript N, when the quadrupole's matrix has been modified to NQN. This matrix is of the quadrupole with changed strength. MR, rest of the matrix in this synchrotron will remain same. So MR is same as is here. So we can put the value of MR. Here you can say that MR is equal to MQ inverse M. So let us put this value of MQ here. So you will get the result MQN, MQ inverse M. Here it is the quadrupole matrix with change in strength. It is the quadrupole matrix inverse with correct strength. So quadrupole matrix with the correct strength is 10KL1. Here again we are considering the thin quadrupole, means we are working in the thin lens approximation. So inverse of this matrix will be 10 minus KL1. Only sign of this element has been changed. Determinant of this matrix is 1. Now if quadrupole strength has been changed, say change is delta KL, so new matrix of the quadrupole will be 10 KL plus this change and 1 here. So we now have one turn matrix under the changed quadrupole strength. It will be like that. This will be the matrix from here. This is the matrix from here, and it is the one turn matrix when there was no strength change or quadrupole has the correct strength. Now when quadrupole has the correct strength, we have seen that one turn matrix can be written down in this fashion: cos phi plus alpha sin phi, beta sin phi minus gamma sin phi, cos phi minus alpha sin phi. Here the twist parameters alpha, beta are at the location of the quadrupole which we are considering. So this one turn matrix, if multiplied by these two matrices, we will get the new one turn matrix with changed strength. And now suppose due to changed strength of quadrupole, beta has been changed to beta n, alpha has been changed to alpha n, and phi phase advance becomes phi n. The new one turn matrix can be written down in new changed parameters like this: cos phi n plus alpha sin phi n, beta sin phi n, because still one turn periodicity is there. So one turn periodic matrix can be written down in this fashion. So if we compare the elements of LHS and RHS, we can get the change in tune due to delta P or change in strength. There should be a matrix. This is written wrongly. There will be A, B, C, D, which is the multiplication of 10 KL plus delta KL 1 and 10 minus KL 1. So this produces a matrix ABCD, and this will be here. And after multiplying these all things together, we will get this matrix. So here you can see that this element is still cos phi plus alpha sin phi, but this element now contains beta sin phi multiplied by the error of the quadrupole or strength changes in the quadrupole. Now if we can compare the trace of these two matrices, now these two matrices are the same. So we can compare the trace. When we will compare the trace, only cos phi will be there. So in the new lattice LHS side, we don't have any trace parameter, and it will be easier to obtain the phase change. And phase, if we obtain the phase change, we can obtain the tune change. And if we can obtain the tune change, chromaticity is defined by the change in tune. So 2 cos phi n will be 2 cos phi plus delta KL beta sin phi. This is the trace of this matrix. This can be written down as 2 cos phi n minus cos phi. It will be delta KL beta sin phi. And this cos C minus T formula is applied here. It will give sin phi n, and sin phi plus phi n upon 2 is equal to 1 by 4 delta KL beta sin phi. Now because we are assuming that energy spread not much, means delta P by P is a smaller value. So change in strength delta KL will be also a small number. And that's why the change in phase will also be smaller. So we can write down sin delta phi by 2 and sin phi plus delta phi by 2 is this. Now using the approximation that delta phi minus phi n is small. So sin delta phi by 2 can be approximated as delta phi by 2. And here we can neglect the delta phi in comparison of the 2 phi. So 2 phi by 2 will be sin phi, and this will be RHS. So now sin phi and sin phi cancels out, and you have delta phi is equal to minus half delta KL beta. Delta phi is basically the phase advance over the one term. So it is related with, means number of beta tone oscillations over a one complete turn can be obtained, which is a tune is equal to 5. So phi can be written down as 2 pi mu. So delta phi can be written down as 2 pi delta mu. So this is written here, and this equation, using this equation you can get the delta mu. So change in beta tone tune is beta at that location multiplied by the change in strength. Now if quadrupole has higher beta at this location, the chromaticity will be higher because delta nu will be higher in that case. Now this delta KL we have calculated earlier that this will be equal to KL delta. This delta is delta P by P. So this will be the chromaticity. Now you can see that this chromaticity is calculated only for one quadrupole. So for calculating the whole lattice, we have to integrate this formula over the entire circumference. So this is the chromaticity for the synchrotron or a complete ring. Now you can see here that K into beta, this combination generates the chromaticity. Means higher strength of the quadrupole will generate higher chromaticity. Means if a lattice has stronger quadrupoles for stronger focusing, it will have large chromaticities. And if beta is higher at the location of the quadrupoles, then it will generate the higher chromaticity. Now we have seen that in the case of quadrupole, the kick for the off momentum particle was KLX delta. Means kick proportional to x into delta. And for a sextupole magnet, this kick was MDLX delta. So you can say MDL of the sextupole is equivalent to KL of the quadrupole. So if KL of the quadrupole generates this chromaticity, then MDL will generate a contribution using M d beta. So this is the formulation of the chromaticity when sextupoles are also introduced to correct it. Now you can see that this is the natural chromaticity because it is the chromaticity generated only by the quadrupole. So this is the natural chromaticity. And it is the chromaticity when we consider sextupole also. And now properly choosing M, we can cancel out this K beta. So by properly choosing the strength of the sextupole magnet, we can make this integration 0 and chromaticity will become 0. In this fashion, sextupole magnets can be used to correct the chromaticity. Now you can see several things here. Suppose we want to produce some MD beta combination for a given K beta. So if sextupoles are placed at higher dispersion and higher beta function location, then M will be small. Means a small value of M can generate the required K beta if D and beta is large. D and beta are the dispersion and beta tone function at the location of the sextupole. So sextupole should be placed where the dispersion and beta function is large. Because if sextupoles are going to be stronger, we have seen that these magnets will generate a nonlinear effect, and that nonlinear effect will be also stronger, and nonlinear instability in the machine can be there. And under this strong sextupole, lattice optimization becomes a very typical job because it involves nonlinear dynamics. So we want that smaller strength of the sextupole should do our work. So in this fashion, sextupole should be placed at the location of higher dispersion and higher beta function. Now one question can arise here. If in vertical plane there is no dispersion, then how the sextupole magnets can correct the vertical chromaticity? And the answer is that because you have Bx is equal to Sxy for the sextupole magnets, and if you put X as X beta tone plus D delta Y, so we will have a term D into Y delta. So horizontal dispersion can be used for correcting the vertical chromaticity also, and this is only because sextupole magnets generate coupling between these two motions, horizontal and vertical beta tone motion. So using that coupling, the horizontal dispersion can also be used to correct the vertical chromaticity in a synchrotron. Now when we introduce these sextupole magnets, the dynamics becomes nonlinear, and we have to solve the nonlinear Hill's equation in that case. And in the presence of nonlinearity, up to certain amplitude of the beta tone oscillation remains stable. Outside that amplitude, beta tone oscillation becomes unstable. So nonlinear dynamics or introduction of the sextupole actually separates the whole space into stable zone and unstable zone. And outside that stable zone, beta tone motion will become unstable. And as the sextupole becomes stronger and stronger for correcting the larger and larger chromaticity, this stable space shrinks down and running the machine becomes difficult. So an accelerator designer optimizes the sextupole scheme for enlarging this stable area for the beta tone motion. This stable area is known as dynamic aperture in the accelerator channel. So introduction of the sextupole lowers down the dynamic aperture, and an accelerator designer has to optimize the sextupole scheme and lattice in such a way that we get the larger dynamic aperture. So if we introduce the sextupole for correcting the chromaticity, whole Pandora box of the nonlinear dynamics opens, and it becomes a difficult problem to optimize the sextupole scheme when we are introducing very strong quarter pole for tight focusing. Next lecture, we will cover a completely new aspects of the dynamics, that is the longitudinal.